Right, we are going. And last time we left off in the middle of something. We're talking about fractions, properties of fractions, how to add and subtract them. And I mentioned that fraction is only 0 if the numerator is 0. We kind of left it there. So let's pick up at the same place and start talking about a very important idea. It's called the least common denominator. Or LCD. Sounds like a drug, but man, in class we're all doing LCD, man. Awesome, man. Yeah. Okay, what's the LCD? Given a set of fractions. The LCD is the smallest, that's why the word least is there, number that all denominators can divide into. Without leaving a remainder. So it divides into it evenly, so the result of doing this division will leave you with a whole number. That's what it is, finding the LCD. Step 1, you must find the prime factorizations all of the denominators. Now that just means you're going to factor the numbers in the denominator and you want to factor it into prime numbers. You might remember a prime number. This is just a positive integer greater than 1 that the only integers that can divide into it, the only positive, it's just an integer, the only positive integers that can divide into it are itself and 1. We want to factor a number into its prime factors. This is called prime factorization. And there is a theorem, which you don't need to know, it's called the fundamental theorem of arithmetic, which basically says every integer has this kind of factorization. So whatever integer you're looking at, there's a way to factor it as a product of prime numbers. 2. Once you actually factor each of them, the LCD is the product of all primes from step 1 raised to the highest powers to which they appear. Okay, let's do an example. LCD of 16 and 12. We want to find the smallest number that both of those guys will divide into. So what we're going to do is we're going to find the prime factorization. I want to factor this up into so that I can write as a multiplication of prime numbers. And for some numbers you start small, the smallest prime number that you know can go into it. So the first few prime numbers are 2, 3, 5, 7, skip 9, 9 is not prime, then 11, etc. We can see that 2 goes into this because it ends with a 6. If anything ends with a 0, 2, 4, 6, or 8, we know it's a 2 can divide into it. So I would divide 2 into that, and I would be left with 8. And I realized, oh, I can divide 2 into that again. So I divide 2 into the 8, the result is 4, and I can divide 2 into that. So that's 2 times 2 times 2 times 2, or this I can write as 2 to the 4th. This is the prime factorization of 16. I can think of it as a multiplication of 4 2's, and 2 is a prime number. I would do the same thing with 12. So I would say, okay, I can get a 2 into that. That's going to be 2 times 6. And I can get a 2 out of 6. That's going to be 2 times 3. These are all prime numbers, 2 and 3. And so this one is 2 squared times 3. That's the prime factorization of 12. Now once I do that, my LCD will have the following form. Every prime number that shows up, I'm going to write them down. In this case, it's 2 and a 3. And then I'm going to identify the largest powers to which these guys appear. And as you can see here, the largest power of the 2 is what? That's the biggest power for the 2. So that's what I'm going to write here, to the 4th. 3 only shows up in one position, so the largest power here is of course going to be the 1, and so that's what I put here. This is going to be the LCD. It's going to be 16 times 3, which is 48. That's your LCD. That'll be the smallest integer that both 16 and 12 can divide into and not leave a remainder. Using the LCD. This can help us add fractions easier. Now, recall from yesterday I told you how to add fractions. If I have A over B plus C over D, then this is by definition you multiply this by this, multiply that by that, divided by this, right? That's how you add two fractions. That will always be the answer. There's going to be a problem though, and I'm going to show you what it is. And the problem is basically going to be, sometimes that's not going to be the most efficient or the reduced form. It's definitely going to be the answer, but you might have bigger numbers than you need to have. So let's do an example. 3 over 16 plus 5 over 12. I want to add these two fractions. Now, I can strictly go by the definition that I mentioned yesterday. So this is, I'm going to use the definition. At the moment, I'm not worried about the LCD. But by the definition from yesterday, what I can do is I can multiply this by this. Put the sign back. So you literally follow whatever sign was in the middle and you put it back. Then I can multiply this by that. All over. Now I can multiply this by that. And that's actually the answer. Now that might not be the nicest form of the answer, but that's the answer. That's how you add fraction. That's the kind of brain dead way to add a fraction. Just follow this definition. But let's actually simplify this a little bit. Let's reduce. Let's go through this. What's 3 times 12? 36. 5 times 16?
80. That's just 80.
80, yeah. 16 times 12?
192.
192. Awesome. He's fast with the arithmetic. Like even I don't do that fast in my head. Eventually you get to a point where you're over arithmetic. I just don't want to. Like every time I'm at and I have to do some arithmetic on the board, I'm like, oh, my brain just skips out. Like, I don't want to do this. That's why I like ask you guys. You know, it's under the guise of I'm testing, but really I'm asking because I'm too lazy to do it myself. Which is sad, because when you tell someone you're a math person, arithmetic is always how they test you. You ever notice it? Oh, you're a math person? Calculate the tip on this check right now. Like, I'm not a calculator. I'm not. Math isn't about arithmetic, okay? This is pre-calc. Math goes beyond that. But whatever. I digress. How can we finish this up? We can add the 36 and the 80 and we would get what?
160.
Okay, now let's reduce that. Well, we can take 2 into this, right? That's even. And you remember how to do that? 2 into 11 goes 5, remainder 1. 2 into 16 goes 4, right? 8. See? Okay. So that's 58. Do it again. 2 into 19 goes how many times? 9. Remainder 1. 2 into 12 goes 6. We can go a little further. Into this goes 2 times. Remainder 1. 2 into that goes 9. 2 into 9 goes 4 times. Remainder 1. 2 into 16 is 8. Can we reduce that anymore? Right, no. And that's your answer. Now, I let you guys suffer through that. Well, I allowed myself to suffer through that to draw a comparison to what is possible when we throw the LCD in the mix. Let's look at this again, but using the LCD. So let's look at the same problem. And again, we're going to be adding things other than fractions where they're purely numbers, right? They're going to be mathematical expressions here. But understanding how the mechanism works with numbers will help you to understand that mechanism a little bit better. So here is how you would use the LCD. Basically what you would want is you would want the denominators of the individual fractions to become the LCD, because we had this rule that I told you yesterday that if the denominators are the same, then you can just add the tops and then leave the bottom alone, right? So that was a rule. I probably switched the B and the C there, but it doesn't matter. So now the idea is whenever we want to get that to happen, it's very convenient for us to not multiply by anything bigger than we need to. So what we're going to do is we're going to want to multiply these denominators by whatever I need to multiply them by in order to get the LCD in that location. So remembering that this here was 2 to the 4th, because we did it. Remembering here that this was 2 squared times 3, right? And remembering that the LCD in this case was 48, which is 2 to the 4 times 3. You don't always have to do the prime factorization at this stage, but it's probably, if you can't see what the LCD is, factoring is going to be nice. And noticing the factoring stage will help you with the algebra kinds of combinations. Right? So basically I'm going to multiply these denominators by whatever is missing in order to get up to here. Okay, so that's the goal. So now the LCD is 2 to the 4 times 3, which means this denominator is missing what? It's missing a factor of 3. It's missing the 3. So what I'm going to do is I'm going to multiply that by 3. So I'm going to multiply this by 3, right? Well, you can't just multiply by 3 in the denominator, right? Because now you're actually dividing something by 3. So we multiply the denominator and the numerator at the same time by 3. So this is equivalent to multiplying by 1, so I'm not changing the value. All I'm doing is making the denominator behave a certain way. And so now that will make this denominator 48, right? The numerator will just be 3 times 3, which is 9, which we know how to multiply fractions. Then we're going to move over here. Now what's missing from here? Well, the LCD is 2 to the 4th, which means I'm missing a 2 squared, or a 4. So what I'm going to do is I'm going to multiply this by 4 in the denominator to make that a 48. But I have to multiply by 4 in the numerator as well, so that I'm not changing the value. And again, this is going to be 48. And the top is going to be 20, right? Now, the more you practice, of course, the quicker you'll get with this, but ultimately here you can see now the denominator is all 148, so I can apply that rule and just add the tops, which I get 29, right? Which is a lot faster and a lot easier, right, psychologically, because you're not dealing with these huge 192 and 116. You can get to the answer a lot quicker, right? So this idea of factoring things and then using the missing factors to figure out how to combine the fractions is very convenient, and it can work even when you don't really have numbers here. And that's going to be now kind of how we want to do things. So if I give you these random expressions or rational expressions, because they're ratios, basically the idea is you're going to want to start factoring stuff so that you can do this kind of game and get away with it with the least amount of pain possible. I want to do a few more examples with you of what we call complex or compound fractions. So we are going to do these examples here. Or maybe I'll work through one with you and then I'll give you 3 more examples of it. Let's look at compound fractions. AKA complex fractions. Even though that's probably a bad name for it, but I've seen textbooks call it that. So depending on where you're reading it, it's going to be that. So this is when you have nightmare upon nightmares, fractions within fractions. So example, let's look at this one. Simplify 3 over 16 minus 5 over 12 all over 3 over 4 plus 2 over 3. So look at that scenario. Now I want to do it one way. Do it without the LCD for a comparison, and well, maybe when adding the fractions I'm going to use the LCD. So let's do it one way where method 1, you can combine fractions in numerator and denominator separately. Then divide the resulting fractions. Again, this is probably the straightforward, I don't want to think a lot kind of way to do the problem, and it's fine to do it, but I'm going to show you another way that seems to make it a little bit easier. So that's one way you can think about it. So at this point, I think most people would agree to add 2 individual fractions, this would be the preferred method. So let's actually start by doing that in the top and the bottom. So here are some fractions in the top, here are some fractions in the bottom in the numerator and denominator. Let's actually combine those separately first, which is what some people might think of doing, and it's perfectly fine. So how do you combine this and this? Well, we play the same game. Remember that the LCD here was 48. So I'm going to multiply this by 3 over 3, multiply this by 4 over 4. So that becomes 9 minus 20. So this will be 9 over 48 minus 20 over 48. Now, for the bottom, what is the LCD here between 3 and 4? 12, right? And it's easier to see this one, but of course, if you can't think of it, just do the prime factorization like I did before. So a 3 is missing from this denominator, and a 4 is missing from that denominator. So now I would get 9 over 12 plus 8 over 12. That allows us to combine these guys. So 9 minus 20, minus 11, and 9 plus 8, 17. And so we first combine the fractions in the numerator and denominator, and now what we're going to do is we're going to take this function, divide. this fraction, divide by that fraction. So what do? Keep, change, flip, right? You keep the top one, change the division to multiplication, and flip the bottom one. Now at this point, I'll probably start reducing before I combine. Kind of a pro tip there. Reduce before combining. That will kind of make your life a lot easier. So if it's possible to reduce it before you start multiplying things out. So rather than multiply 48 by 17, doesn't sound like a lot of fun, I can actually reduce the 12 into the 48. So now I only have to multiply 4 by 17. 11 doesn't go into 17, 17 is prime, so what we're going to do now is just multiply across. This is minus 11 over 60 what? And I don't think that's, and so that would be the answer. Here's an alternative. And probably the more efficient way in general. I would say this is recommended, but that's just it. It's recommended. In general, if you do something correct, I don't care if you do it the way that I show you, or I'm not going to force you to use one method in general. But I'll point out things that I think will save you pain in the long run. So you can do it that way, or you can just choose to do it the way you've always done it. It's up to you. Just make sure whatever you're doing, it's correct. So so here's the alternative. Let me actually describe it. Is to find the LCD of all fractions present. So that's both in the numerator and denominator. So once you find the LCD, you're going to multiply the big fraction by this fraction, which is again 1, but it is going to be convenient in a particular way that we will see. So you're going to find the LCD, you're going to multiply the big fraction by that, and then, of course, do your old simplification. Reduce things, combine things, etc. So here's how that would look. So let's say 3 over 16 minus 5 over 12 all over 3 over 4 plus 2 over 3. Now what's the LCD of everything? So this means, yeah, so I'm looking for the LCD of 16, 12, 4, and 3. Now it turns out 4 and 3 goes into 12 and 16 and 48 already. So 48 is still the LCD here. That's the smallest number that these two guys will divide into, and the 4 and the 3 automatically divide into that. So here is what we can do, is I'm going to take that thing, and I'm going to multiply by 48 over 48. And you're going to see how I apply this strategy with algebra involved as well. So what's going to happen at this point is you're going to multiply, which means distributive law is going to take effect. So you're going to take the 48 and multiply each of these fractions here. Now when you multiply those, what do you notice is going to happen? If I take 48 times this, what's going to happen? This denominator is going to cancel, right? I can literally divide the 16 into the 48, right? Because it's the LCD. So if I multiply this by the 48, the 16 is going to go into that 48 how many times? 3 times, right? We did that, it was 3 times, all right? So it means that this reduces to 3 times 3 in this position. Now if I multiply this by 48, the 12 is going to cancel into the 48, leaving the remainder 4. So then that will be 5 times 4 over, multiply this by 48, 4 goes into 48 12 times, right? That's going to be 3 times 12 plus divide this into that, the 3 is going to go into the 48. And how many times? So notice here we get to a simpler fraction in one step, right? And now it's just a matter of multiplying these guys out. So that's 9 minus 20 over, that would be 36 plus 32. That's minus 11 over 16, which, as you can see, was the same thing. So it's just an alternative, and when you're not dealing with numbers specifically, I think this method is a lot easier to digest. But when we deal with rational expressions, you're going to see how it all plays out. Just understand how it works with numbers. Once you understand the foundation, how the basics work, you'll be able to apply it to more and more complicated examples. Now try these by a method of your choice. And all of these, the goal is to simplify, reduce. It reminds me of those memes that go, oh, example in class, 1 plus 2 equals 3. Example on the test. Given this ruler, calculate the mass of the sun. Like I show you guys, oh, you just do this with these numbers. It's so awesome. And then they're like X and Y's out of nowhere. Try to apply the same principles though. Again, I think you'd see similar things like this in algebra class, so I'm kind of confident that I can kind of push you guys a little further than the example I did. Do you guys remember what the difference quotient is? I mentioned this on day 1, but I mean compute this expression here. guys like 6 minutes to do those three. It's a little bit of a rush, but I believe in you. let's see what we got. Okay, someone tell me what you did here.
LCD is X, Y.
Okay, so here he's doing the LCD method. Right? Now, you don't really know what X and Y are, and so it's probably a little bit premature to call this the LCD, because technically you can't really know, but that would be the best guess. If you kind of think of X and Y like they're prime numbers, those are the factors, really. So X appears to the power 1, and Y appears to the power 1. You think of those guys as if they were prime factors. So the algebraic factors, you kind of treat them like the prime numbers that you would have treated in the numerical example. So what do you do with that?
You multiply both sides of the function by X, Y.
Right, so you just multiply by xy over xy. So the distributive law is going to take effect. So this entire expression is going to multiply that, then it's going to multiply that, and then this entire expression is going to multiply that, then it's going to multiply that. At the end of the day, what happens in the first situation?
You're missing Y, so it's Y times Y.
The x's cancel, and so you just have y squared minus, in the second situation,
You're missing X.
the y's cancel, so you just have x squares over.
You're missing X. So
Here, the y's cancel and you're left with x.
and then Y.
Here, the x's would cancel and you're left with y. Okay, so that would be, you go from a complex fraction to a simple fraction in one step by multiplying and dividing by the LCD. We can go further. What do we do?
You simplify.
You can simplify that. Yeah?
You can factor the numerator out.
Uh-huh. Why would
So it would be y plus x and y minus x.
Right, that's the difference of squares. Then,
Cancel.
be careful, y minus x and x minus y are not the same.
So you can take out a -1.
You can factor out a -1 from one of them before. So for example, instead of xy, I can think of this as minus y times x, right? Factor out a -1 from the denominator, that makes these guys the same. So when these cancel, there's going to be a negative sign left over. And so we would end up with minus y plus x. And that would be the answer. Yes?
Is it okay if I distribute?
Yeah, minus y minus x is fine. And you can also write it as minus x plus y or minus x minus y. Those are fine, but I don't see any point in actually taking that extra step, so I would leave it here. Alternatively, here's another way you could have done it. Personally, I think this way is the best way, multiplying and dividing by the LCD, but you could have also done it the other way. So let me show you something else. You could do the combining fractions in the top and bottom at the same time. So what you would do is, because I don't really know what these numbers are, I'd probably do the definition here, or y times y is y squared, x times x is x squared, over x times y, over x times 1 is x, y times 1 is y, over xy. So now you'd have that. So now you would have this, keep, change, flip. This would cancel, and then you'd end up in this situation, right? So you could do this, perfectly valid, perfectly legal, just notice that you will take longer to get to this point, and anything that takes longer, there's more opportunity for you to make a mistake, drop a negative sign, or anything can happen, right? When you're rushing and you're anxious. So, not illegal, you do it this way, you do it correctly. I'm not going to downgrade you for it, but just be aware that you have to factor in some extra time and you have to be extra careful. Did I put that eraser? Let's do B. Okay, what about B? What do we do for B? Yeah?
I multiplied what is it, the LCD was a squared for both the numerator and the
It's a squared.
denominator.
One thing you can notice is that you can think of this 2 as being over 1. So all your denominators are 1a and a squared. And then using our LCD rule, a squared is going to be the LCD. So in here, the LCD is a squared. So what I'm going to do is I'm going to multiply and divide by a squared. This is going to multiply that, multiply that, multiply that, multiply that, multiply that, multiply that. So here I would get 2a squared plus, here the a's are going to cancel, so I'd have 5a minus, here the a squared cancels the a squared, so I have minus 3. Then 2 times a squared, a cancels, so I have minus 5a, and the a squares cancel, so I'm left with plus 2. So we're now in this situation. How do we reduce that? Factoring. So we'll probably talk about this at some point, how to factor this, things of this sort, if you forgot, but as for anyone who remembers, how do you actually do this? Yeah.
So it's like 2 bubbles, and then the factors of the A term and the C term have to add to the B term, but also multiply to them.
So you're doing the AC method.
Okay.
Right, so I'll probably talk about that a little bit. I'll talk about that later. But this one you can do a little bit quicker, so I'll just do it. So because 2 is prime, that's pretty easy to know how to get the A. So you have 2A and A, right? So now you know you want to get a 3. There's only one way to get 3s, 1 and 3. So you know it's either a 1 and 3 or a 3 and a 1. How do you know what choice you have to make? Well, the middle numbers and the outer numbers must add up to the original middle number. So notice that if I put a 3 on this side, I would get 6a. Put the 1 here, I would get 1a. And then I ask myself, can I get a minus 5 from a 6 and a 1? The answer is yes. Make sure it's a minus 6 and a positive 1. And that's how you factor.
Wouldn't it be a positive 1
You're doing the top first.
Oh, I was looking at this.
Yeah.
It's a plus 5, so I want a positive 6 and a negative 1. We're doing the top one.
Yeah.
So this would give us 6a, this would give us minus 1a, that gives us the 5a. And so that's kind of a shortcut than the AC method, but I'll talk about the AC method at some later point. So I'm going to discuss factoring with you guys already. It's going to involve reminding you how to factor quadratics. We're going to do the same idea here. To get a 2a squared, 2a and a works. To get a 2 and a 1 is going to work. So I know the 1 and the 2 has to go in a certain position. Now I'm going to put it in the wrong position on purpose first, so you can see what would happen if you go wrong. So let's say you thought the 2 goes here and the 1 goes here. Something is going to go wrong there. For 1, you can notice that this makes 2 a common term in the first factor, which means you should be able to factor out a 2. But if I can factor out a 2 here, I would have been able to do it there, and you can't factor out the 2 out of the 5. So that's definitely the wrong choice. Another way you're going to notice that you did something wrong is if you do this thing. If you multiply these 2, you get 2a. If you multiply these 2, you again get 2a. And how are you going to use 2a and 2a to add up to minus 5? You can't do it, right? So then you're going to realize, oh, that's wrong. It must be the other way. And so I'm going to put the 1 here and the 2 here. That way now I get 4a and 1a. And I can get a minus 5 by making both of them negative, right? Minus 4a minus 1a gives me the minus 5a. and that will be the factors there. Now, that's a common term, so this cancels. And I'm left over with a plus 3 over a minus 2. And we have the last example. I did a similar example to this on day 1, but again, functions is probably something I'm going to talk about at some other point and remind you how to actually plug these in. But I did mention something like this before. Okay, so if this is your f of x, what does this look like? What would f of x plus h be? No. Right, so remember how the function works? Whatever is inside the parentheses goes in this position, right? So this is in the parentheses, therefore that goes in that position where there's a square on the outside of it. So you actually have x plus h squared, all squared, right? So you don't just add the plus h at the end. The x plus h must replace every x. So that would be the first part. Minus the second part is just f of x, which is just a copy of this. All over h. So let me just rewrite that in case this isn't clear. So far we have 1 over x plus h all squared minus 1 over x squared all over h. How do you simplify that? What's the LCD? How would the x squared factor into that? So remember how the LCD was created. You look at all the factorings of the denominators, which these are already factored for you. There's a base x raised to the power 2, so there should be an x in here. There is also a base x plus h raised to the power 2, so there should be a base x plus h in here. Then you're going to look at what is the highest powers to which these guys appeared. As for x, the highest power that appeared was a 2. For the x plus h, the highest power that appeared was a 2. So the LCD is x squared times x plus h squared. So what I'm going to do is I'm going to multiply this by x squared times x plus h squared over x squared times x plus h squared. And again, distribute it all. Distribute it all. So what happens in the first situation? The x plus h squares are going to cancel, and we're going to be left over with an x squared. Minus, in the second instance, the x squares will cancel. Now I'm going to be left over with an x plus h squared. Parentheses, very important here. In the denominator, I'm just going to multiply this across. So we have that. Now, pro tip here, you want to simplify a fraction, never expand the denominator. You always want to leave the denominator in a factored form. But no such rule applies to the numerator. Ultimately, I think I mentioned this already, but I'll mention it again. Canceling the h is the goal here. You want to keep simplifying until you actually cancel that h. But in general, you'd want to know how this can be reduced anyway. So what would be the next step here? We can't expand the denominator, or we shouldn't. So what can we do with the numerator? Expand it, what would it look like? So it's minus And you really need to remember the parentheses here because that's going to. Okay, so what does the x plus h squared expand to?
Plus 2x
Right, we had that formula. So we have that. Now the negative sign is going to be distributed. The x's die. And we can cancel this h, right? Right?
No.
No, cannot cancel the h. Do that, I kill you! Okay? Anyone knows where that's from? Huh? You know? It's a classic. From a Jeff Dunham stand-up. Not very PC, but whatever. It was made a long time ago. But canceling h is the point, so how can I get that done? Factor. H is a common term, so the first thing I would do is factor that h out. I could. Nothing wrong with it. Over, now h x squared times x plus h squared. Now the h's can cancel because everyone is multiplying together. So now I have minus 2x plus h over x squared times x plus h squared. And that's pretty much the simplest you can get. Okay. And jump to another section of this, well, section. We're still in the same section in the book, actually. Regurgitate some definition about sets. Remember, a set is a collection of objects. That's all it is. So in math class, the objects are often numbers and notations. So some things you can notice, we can name sets. Usually, but not always. With, although usually probably just implies not always anyway, uppercase letters. So I can say A is the set of positive integers between 1 and 10. I could say strictly between 1 and 10 if we want to do it that way. So I can actually name a set. There's also something called the roster method. And this is listing the elements of the set. So the individual objects, we call them elements. We can list them in these curly brackets. So for example, here I can say A equals 2, 3, 4, 5, 6, 7, 8, 9. I can write down a list of all these things and I put it in a squiggly bracket above. You can use ellipses to indicate a pattern, and this usually happens if it's impossible for you to list everyone or you just don't feel like it. So, for example, here I can say if B equals all positive integers from 1 to 1,000. Now, you could technically list all of that, take you a while, but why would you want to do that? You could say B equals 1, 2, 3. You get the idea, 1,000, right? So you don't have to list everything. And sometimes you might not even be able to list everything even if you wanted to. So you might have recalled, like I defined the set n, so this is the set of natural numbers, and we wrote it as 1, 2, 3, dot, dot, dot. As in, you get the idea. It continues, like, forever. So you put the ellipses at the end to say it continues forever. You put it in between two things to say, oh, whatever pattern you saw was happening before keeps happening until you get to this point. The symbol this means an element of or member of. So for example, I can say 3 is an element of the set of natural numbers, right? This is in that set. 3 is an element of big N. And this is just a general principle, actually. Striking through typically means not what you struck through. Right? It's just a math person's way of saying, I don't mean that. I mean the opposite. Right? So for example, you've seen this before. This is equal, this is not equal. Right? You just strike through it. That principle is like, it's a kind of standard thing to do. So if I write this, it means not an element of. So I can say -5 is not an element of the natural numbers. Right? That's a statement I can make. What else can we say? I could also do another example. So I defined C for you before, and I told you we won't use it, but I just actually wanted to use the notation. And I wrote it out in words. I can actually write a shorthand. And so, remember, it's things that looks like A plus IB. Using these symbols that I've mentioned before, I can now say something like A, B are real numbers, right? This statement means these guys are both real numbers. Yeah. So I could have a shorthand for that. So this line means such that, and this here is a condition after the such that must be fulfilled. and what happens before is the form of the elements. Or some sort of description, and that's a standard way to write down some sets. Such that sometimes we use a colon depending on the source you're looking at. So what I wrote above is equivalent to writing a plus ib colon ab are real numbers. There are things called unions and intersections. If A, B are sets, their union, A, U, B, that's how you actually write it down, is defined by it's the set of all x, so I'm going to use that notation there, such that x is in A or x is in B. So find all the things that are either in this set or that set, or both. Right? So this is the inclusive or, and then you write all those guys down.
Thank you.
Their intersection, which is written as A intersect B. Is given by A intersect B equals the set of all elements such that x is in A and at the same time x is in B. It's called the intersection. Example. Say A is 1, 2, 3. B is 2, 4, 6. C is 5, 7, 9. Then, if I say A union B, basically I'm going to collect everything that's in A, B, or both. So 1 is in A, so that's definitely here. 2 is actually in both. You write down once. 3 is in A, so that's there. 4 is in B, so that's there. 6 is in B, so that's there. That's the list of things that are, you can find it either in A or B or both of them. If you look at A intersect B, what is that? 2. 2 is the only thing that is in both of them at the same time. What if I were to look at A intersect C? There's nothing. You can write literally nothing like that. This, by the way, is called the empty set. So your collection, your set can be empty. It's also, another notation is for a circle with a strike through. So that's a common notation. So whenever you see that in a math book, it means the empty set. You can see this or this. Older textbooks tend to use this, newer textbooks tend to use that. You guys remember the inequality symbols? Well, you should. good. Let me remind you. This is, when read from left to right, this is greater than or equal to. This means greater than. Not equal to is implied. This means less than. This means less than or equal to. So for example, I can say 1 is less than or equal to 2, which is true. I can say 3 is greater than minus 7, that's true. Technically, you can even say something like 3 is not greater than 4, but that's very rare. They would just not make the statement in the first place. One thing that's going to be important to put this all together is something that we call interval notation. So starting next class, I'm going to ask you to use interval notation to do things. And so let's just wrap up with that. So inequality notation. So I can say something like x is greater than a, or x is greater than or equal to a. X is less than a. X is less than or equal to a. I can do x is between a and b. I can say x is between a and b but potentially equal to b. I can say x is between a and b potentially equal to a. I can also say x is between a and b potentially equal to either of them. These all have a corresponding notation called interval notation. This one is open parentheses a comma infinity. Goes from a to anything bigger. This has a bracket, which we think of as the closed parentheses going to infinity. This means a or anything less going down to negative infinity. This means anything less than or equal to a going down to negative infinity. This means strictly between a and b. So it looks like a coordinate, but in a context you should know that it's not a coordinate. Here, here, and here. It's that. So writing down these statements is the same as you writing down those statements. And there will be times when I ask you specifically to give an answer in interval notation, which I will next time. So we'll stop there. I'll see you guys on Monday.